Hi everyone, welcome to another calculus video. In this video you will learn how to use the technique of substitution, or as it is sometimes called U-substitution, to evaluate integrals. Now you already think of integration and differentiation as inverse processes. Now the chain rule is a technique of differentiation. With substitution you have a technique of integration specifically designed to reverse the chain rule. So how do you know when substitution is appropriate? Well, we'll find out more in the examples, but generally, you might recall that when you take the derivative of a composite function, you need to multiply the derivative of the outer function by the derivative of the inner function, right? Now, substitution, therefore, would be appropriate to use when you actually notice that the integrand, or that expression that's to be integrated, resembles the product of a function and its derivative, right? Now, I say resembles because it won't necessarily be an exact match. Let's take a look at a couple of examples here in 11.3.1, and maybe this will give you a better idea of how it works. So what I have here is the integral of 2x times the root of 1 plus x squared dx. The dx here really means, in terms of x. I notice that the radicand, the 1 plus x squared, has a derivative of 2x, which is precisely what I have here. So this looks like it might have been the result of chain rule, right? If I were to take the derivative of the antiderivative. So let me just do this. So I'm going to make a substitution, and I'm going to say u is equal to 1 plus x squared. Okay, so then the derivative of u with respect to x would be equal to 2x. Okay. So then I'm going to take this derivative expression, I'm going to write it with du isolated. So du equals 2x dx. Okay, and now I'm going to box that off. Okay, because this is information that I will use in subsequent steps of this technique. Okay, so now I'm going to focus on what the original integral was. And the original integral was the integral of 2x times the square root of 1 plus x squared dx. And I'm going to make these substitutions. So first of all, I see 1 plus x squared right here. I'm going to substitute it with a u. So my integral is now going to be actually equal to u square rooted. Okay, and then the 2x dx, this piece right here, well, I actually know what 2x dx is. 2x dx is equal to du, so I can put the du right here. Okay, so I just want to make sure that we're absolutely clear here. The 2x and the dx combined together give you du, right? So I've replaced 2x and dx with du. The square root of 1 plus x squared I've replaced with the square root of u. Why can I do that? Because that was the original substitution that I made. So in fact, all three of these pieces have been replaced in terms of u. Now when you look at the integral that is left, that I come up with, that is a way easier integral to evaluate than the original one in terms of x. So I'm going to continue with this. So this is actually going to be equal to the integral of u to the half du. Okay, which of course is going to be u to the 3 halves divided by 3 halves, or aka multiplied by 2/3. Okay, so this is the antiderivative of u to the half, but of course it's the indefinite integral, so I'm going to add a constant c. Now at this point what I can do is reverse substitute and say, okay, I know that u is actually equal to 1 plus x squared, so really what I have is 2/3 times 1 plus x squared square rooted all cubed plus c. Okay, and that's the final answer. Okay, let's take a look at one other example, and that's 11.3.1 part B. Okay, so this one's a little bit different. I think I might approach this the same way though. I think what I'll do is I'll start with, let's try a different color here. I'll start with u is equal to 3x plus 4, okay? So, I don't know, this kind of worked for me in the previous example where I substituted the radicand for u. Okay, so then du would be equal to 3. Du dx would be equal to 3. Therefore, du would be equal to 3 dx. Okay. All right. So interesting. I don't actually have a 3 anywhere in this expression. What I can do is I can write this as the integral of, let's see, u is 3x plus 4. So again, this is the square root of u. But now I need to replace this dx, and I only know that du is equal to 3dx. But what I can do is multiply each side by a third, right? So if I multiply both sides by a third, I end up with 1/3 du is equal to dx. Okay, so now I have something I can replace dx with, which is 1/3 du. Okay, now I'm going to clean this up obviously a little bit here. So this is equal to the integral of, well, I can actually even take the 1/3 out here. So I'll put 1/3 out here times the integral of u to the half, which is what square root of u is, du. Okay, and I end up with 1/3 u to the 3/2 times 2/3 plus c. Okay, which ends up being 2/9. U is 3x plus 4 square rooted cubed plus c. Okay, and those are your two introductory examples for using the U substitution technique.